Hello and welcome to BBC Learning Zone on BBC Two. With you in the early hours with programmes for schools. More GCSE bite-sized maths this morning, focusing on algebra. We'll be covering equations and formulae, sequences, functions and graphs.
Hello and welcome to GCSE Bitesize. This programme will help you with your GCSE maths exams. It focuses on what you need to know about algebra. There are two other programmes about numbers and measures and shape, space and data handling. The best way to revise with Bitesize is to tackle one topic at a time, working through the video in bite-sized chunks. Each programme is full of useful information with sample questions for you to try. And there's more in the GCSE Bitesize books and on the GCSE Bitesize website at www.bbc.co.uk/revision. There are several exam boards, but the questions will be very similar. Papers are set at 3 levels or tiers by all the boards. If you do the foundation paper, you can achieve from grade G to D. Intermediate covers grades E to B, and higher grades C to A star. Your teacher should have discussed with you which paper you're aiming for. During the programme, we'll add icons to show you which level we're aiming at. This algebra programme is divided into 2 main sections: algebraic methods and sequences, graphs and loci. First, let's look at algebraic methods. This section covers the notation of algebra, different kinds of equations and proportionality. First, algebra notation. To understand algebra, you need to understand the notation, that is, the way it's written down. First, we'll be looking at the symbols we use and how we manipulate them, and then ways of using formulae. First, symbols. Algebra is the language we use to communicate mathematical ideas. The word algebra comes from the work of mathematician and writer Muhammad al-Khwarizmi, who lived in Baghdad in the 9th century. The title of his book gave us the word algebra. In al-Khwarizmi's time, though mathematicians didn't agree on how to write down their ideas, they always used symbols. Only quite recently has there been agreement on which ones to use. Today, if you look at a maths book in any country in the world, the part you will always recognise is the algebra. You need to be able to write, speak and understand this language. In algebra, we use letters to stand for numbers, like x. We do this because either we don't know what the number is, we call these unknowns, or because the number may be able to vary and have many different values. We call these variables. These are expressions in algebra. An expression is any statement using the symbols of algebra. How do we read them? This is 3x. It means 3 x's, in other words 3 times x. This is x over 3. It's a fraction, x thirds, which means x divided by 3. This is x squared. It means x times x. If we add up 3 x's, x plus x plus x, we get 3 x's. That's 3x. If we multiply three x's, x times x times x, then we get x to the power of 3, or x cubed. The small number after the x is called the index number, and this method of writing is called index notation, which you need to know about for the higher tiers. We can use all of the index notation we saw in the numbers section. X to the power of -1 is 1 over x. X to the power of -2 is 1 over x squared. X to the power of a half is the square root of x. We have to be careful with index notation. The index only refers to the symbol it is next to. For example, 2x squared means 2 times the square of x. That's 2 times x times x. If we want to say that the whole 2x is squared, then we must use brackets, which gives 2x times 2x, which is 4 times x squared. We read this expression as 3x plus 1. We can work out or evaluate an expression if we know the value of x. If x is 5, then 3x's are 3 times 5, that's 15. So 3x plus 1 is 16. If we are told that an expression like 3x plus 1 is equal to something else, then it's an equation. Often we can work out the value of x from an equation. For example, if 3x plus 1 equals 16, then 3x must be 15. If 3x's are 15, then each x must be 5. Always set out algebra equations like this, with the equal signs lined up below each other. If both sides of an equation, like 3x plus 1 equals x plus x plus x plus 1, say exactly the same thing, we call it an identity. X plus x is exactly the same as 3x's. Notice the special equals sign we use for identities. There are different ways of showing that something is equal to 3x plus 1. We read a is equal to 3x plus 1, or x maps to 3x plus 1, or f of x equals 3x plus 1. This is a formula, this is a mapping, and this is a function. In a formula, we can find the value of a for different values of x. If x is 6, then a is 3 times 6 plus 1, which is 19. If x is 12, then a is 3 times 12 plus 1, which is 37. This is called substitution, because we've substituted values for x. It works the same for the mapping and function notations. If x maps to 3x plus 1 and x is 5, then 5 maps to 3 times 5 plus 1, which equals 16. Using function notation, we can substitute a value of x. If x equals 8, then we can find the value of f of 8. We say that f of 8 equals 3 times 8 plus 1, which is 25. You need to remember these types of algebraic expression and the difference between them. An equation, an identity, a formula. To solve problems with algebra, we normally have to change statements into different forms. This is called algebraic manipulation. To do this, there's a basic toolkit of algebra you can use. Simplifying, expanding, factorising, rearranging, cancelling, cross-multiplying. We'll go through these 6 tools. First, simplifying. You need to know about simplifying for all tiers of the exam. Simplify a plus a. That equals 2a's, which we write as 2a without a multiplication sign. Simplify a times a. A times a is a squared. That's 2a's multiplied together. It's written a with a small 2. A times a times a is a cubed. That's 3a's multiplied together. It's written a with a small 3. Simplify AB plus BA. AB is the same as BA, so two of them make 2AB. Simplify 5 times A times B. The A times A in the middle is A squared, and we don't need the multiplication sign in algebra. And so we just write 5A squared B. Simplify 5AB plus 3AC, take away 2AB. In this expression, there are 5 ABs. Take away 2 ABs, which simplifies to 3AB. There's also a plus 3AC, which is different, so we can't simplify any further. This leaves 3AB plus 3AC. Next, expanding. To expand a statement, we take the statement with brackets and write it without brackets. This is also called multiplying out. Expand 2 times A plus B. 2 lots of A plus B means 2 lots of A plus 2 lots of B. That's 2A plus 2B. Expand 3 times x plus 2. 3 lots of x plus 2 means 3 lots of x plus 3 lots of 2. That's 3x plus 6. Expand 5 times 2x minus 1. 5 lots of 2x is 10x. Take away 5 lots of 1, 5, makes 10x minus 5. Expand A times A plus B. A lots of A is A squared, and A lots of B is AB. That makes A squared plus AB. Expand A plus 3 times A plus 4. We have A plus 3 lots of A plus 4. That's A lots of A plus 4 plus 3 lots of A plus 4. So we have A times A, that's A squared, plus A times 4, that's 4A, plus 3 times A, that's 3A, plus 3 times 4, that's 12. So each thing in the first bracket is multiplied by each thing in the second bracket. We can simplify the 4A plus 3A in the middle to make 7A, giving the final answer A squared plus 7A plus 12. Next, factorising. To factorise, we take a statement without brackets and rewrite it using brackets. This is the reverse of expanding an expression with brackets. To factorise 3A plus 3B, we first need to see if the same thing is multiplying all of the parts. Here, both parts have 3 multiplying, so we can say they both have a factor of 3. That means we can take the 3 outside the brackets and turn 3A plus 3B into 3 times A plus B inside the bracket. Factorise 8A plus 4B. Here, both parts have a factor of 4 in common. The first part is 4 times 2A. The second part is 4 times B. So the answer is 4 brackets 2A plus B close brackets. This is a bit more complicated. Factorise 4ab plus 2bc. In this one, there's a factor of 2 and of b. The first part is 2b times 2a. The second part is 2b times c. That means 2b can be put outside the bracket to give the answer 2b times 2a plus c. Factorise a squared b plus ab squared. A squared is a times a, and b squared is b times b. So the expression becomes aab plus abb. Both parts have factors a and b. The first part is ab times a. The second part is ab times b. So AB can come outside the brackets to give the answer AB times A plus B. Next, rearranging. At all levels of the exam, you may need to rearrange a formula to make some other part of it the subject. We have A equals B plus C, but we want to rearrange the formula to leave B on its own, to make B the subject of the equation. First, take C away from both sides. That gets rid of the C on the right-hand side and makes the formula A minus C equals B. Now write it the other way round, so the formula starts with the B, which gives the answer B equals A minus C. Here's a higher level example. Rearrange B equals x minus y divided by d to make x the subject of the formula. To leave x on its own, we first multiply both sides by d. That gets rid of the d on the right-hand side. We now have bd equals x minus y. To get rid of the negative y on the right-hand side and leave the x, we add y to both sides. That gives us bd plus y equals x. Finally, write it the other way round to make x the subject. That's x equals bd plus y. Next, cancelling. Cancelling can only be done if you can divide the top and the bottom of the expression by the same amount. With 4ab divided by 2, we can divide top and bottom by 2 without changing the value of the expression. That gives the answer 2ab. Cancel x cubed divided by 2x. Here, we divide top and bottom by x. That gives the answer x squared over 2. Next, a mathematical puzzle. We can find out how it works using the Algebra toolkit. First, watch the puzzle.
I'm going to explore the world of fashion with my friend here, Lizzie, who's very kindly agreed to wear this rather fetching hat. All right, come on, give her a whistle, chaps. Lovely. Way, there we go. Now, this is a brainwashing, mind-reading hat. I'm going to ask you to do some sums in your head. Please do not say anything out loud. You must do it in your head, Lizzie, OK? Right, I want you to think of any number you like between 1 and 100. Okay. You're thinking of it, yeah? Now, could you please double it? Have you done it? Very confident. Add 6.
Yeah.
You've done that. Now, can you halve the answer you've got to divide that by 2?
Yeah.
You've done it?
Yeah.
Now, can you subtract the number you first thought of?
Yes.
All right. Now, think very hard of the answer that you've got. You think very hard of the answer that you've got. At this point, please, I'd like you to very carefully remove the hat. All right, like that. Now, I want you, please, to tell us what number is in your head.
3.
3. Will you please look inside the hat? What can you see? There we are. The number 3.
This time, as the clip plays, we'll write an algebraic expression to represent Lizzie's calculation. Of course, we don't know what number she's thought of, so we'll represent that by x.
Right, I want you to think of any number you like between 1 and 100. You're thinking of it, yeah? Now, could you please double it? Have you done it? Very confident. Add 6.
Yeah.
You've done that. Now, can you halve the answer you've got to divide that by 2?
Yeah.
You've done it?
Yeah.
Now, can you subtract the number you first thought of?
Yes.
All right. Now, think very hard of the answer that you've got. You think very hard of the answer that you've got.
This expression represents Lizzie's answer, but it looks a bit complicated. So first, let's cancel the top and bottom of the first part of the expression. We can divide the top and bottom by 2. And now let's simplify x plus 3 minus x. It becomes 3. The answer is 3, whatever the value of x. So it works whatever number you're thinking of.
At this point, please, I'd like you to very carefully remove the hat. All right, like that. Now, I want you, please, to tell us what number is in your head.
3.
3. Will you please look inside the hat? What can you see? There we are. The number 3.
And finally, cross-multiplying, which you'll need for the higher tier paper. Cross-multiplying works in the same way as adding fractions. Cross-multiply x over 2 plus 3 over x. First, the new denominator is the denominators of the 2 separate fractions multiplied together. That's 2 times x. Now we need to get the new numerator, which is where the cross-multiplying comes in. It's x times x plus 3 times 2. That's x squared plus 6. So the answer is x squared plus 6 over 2x. Cross-multiplying works across an equal sign as well, and is a quick way of rearranging an equation. Cross-multiply the equation 5a over 3b equals 2 over y. On the left-hand side, we have 5a times y, that's 5ay. On the right-hand side, we have 2 times 3b, that's 6b. That's the end of algebraic symbols. This section looks at some practical uses of formulae. Formulae are used a great deal in maths to give general rules. You use formulae to find areas, volumes, and when data follows particular rules. They give a shorthand way of showing how to work things out. In this short clip, archaeologists use a formula to calculate the height of a person from Viking times whose bones have been found.
Let's find out how tall he was. Well, the best bones to use for estimating the height of the skeleton are the leg bones, and you get the most accurate results using those, probably to plus or minus no more than 3 centimetres.
43.9 centimetres.
43.9, okay. We can't just lay him out and measure him from top to toe using a tape measure, for example, because we don't know how much soft tissue we've actually lost. And so that would give us a much greater error than simply using the bones. And what about the tibia?
This is 35.6 centimetres.
Jill uses a formula for calculating the height. This has been worked out by taking measurements from skeletons whose height was already known. By substituting the lengths of the leg bones, the femur and the tibia, into the brackets of the formula, Jill can calculate the man's height.
So his height was 166.64 centimetres. It's just a little bit below average for that period.
In the clip, the formula used to calculate the height of a white male was h equals 1.3 times f plus t plus 63.29, where f is the length of the femur and t the length of the tibia. Obviously, the height obtained is only ever an approximation. But different formulae are used depending on age, sex, and ethnic origin. For white females, h equals 1.39 f plus t plus 53.2, and for black females, h equals 1.26 f plus t plus 59.72. For black males, H equals 1.15 F plus T plus 71.04. And for white males, H equals 1.3 F plus T plus 63.29. Remember to work out the addition inside the brackets first. Using the following lengths for the femur and tibia, find an approximate height for someone in each group with the following bone lengths. For a white female, F equals 34.6 centimetres, T equals 31.4 centimetres. For a black female, F equals 40.3 centimetres, T equals 30.6 centimetres. For a black male, F equals 46.5 centimetres, T equals 36.7 centimetres. For a white male, F equals 43.9 centimetres, T equals 35.6 centimetres. Now, check your answers. For the white female, the formula is H equals 1.39 times F plus T plus 53.2. So first, substitute the values for F and T into this formula to give. Work out the addition in the brackets first. And the final answer is 144.94, which is 145 centimetres to the nearest centimetre. Next, the black female. The formula is H equals 1.26 times F plus T plus 59.72. So, substituting the values for F and T into this formula gives. Working out the addition in the brackets first. And the final answer is 149.054, which is 149 centimetres to the nearest centimetre. Now the black male. The formula is H equals 1.15 times F plus T plus 71.04. Substitute the values for F and T into the formula to give. Do the addition in the brackets. And the final answer is 166.72 centimetres, which is 167 centimetres to the nearest centimetre. And finally, the white male. This time the formula is H equals 1.3 times F plus T plus 63.29. Once again, substituting for F and T. The addition in the brackets gives. And the final answer is 166.64, or 167 centimetres to the nearest centimetre. Here's a clip that involves rearranging a different formula. Even in the hottest countries, the weather is still an everyday topic of conversation, but not all countries use the same system for measuring temperature. In the UK, we use degrees Celsius, or C. But in the USA, for example, they use degrees Fahrenheit, or F. Most of you probably know that freezing point, 0 Celsius, is 32 degrees Fahrenheit. But what about other temperatures? Take a look at this weather report, filmed specially for GCSE Bitesize, using both temperature scales. And then we'll consider the problem in more detail.
Hello. Well, across Europe it's been very frosty, but not just by night. In the northeast of Europe it's been frosty by day as well. Take a look at this. Russia has seen temperatures as low as minus 45 Celsius. That's minus 49 Fahrenheit. Now here the overnight temperature normally is around minus 17 Celsius or 1 degree Fahrenheit. But this, down as low as minus 45 Celsius, is a new record. The reason for that is that we've had clear skies overnight and by day, as you can see showing up here for Moscow as well. It's all due to high pressure, and that high pressure has been a pretty dominant feature for the last couple of days. As you can see, as we go through the weekend, that high pressure stays right across the northeast of Europe, allowing the cold air to push right the way down into central parts. Let's take a look at that, and you can see the blue colours showing that very cold air pushing gradually westwards right across into France as we go through to the middle part of next week. So it's going to be staying bitterly cold there. Well, for Friday then, down in the south, we're going to see quite a few showers. Temperatures in Rome around 14 Celsius. That's 57 degrees Fahrenheit. Further north, well, here getting cooler, only in the 30s or 40s Fahrenheit. As we go through the weekend, let's take a look at Moscow. -9 Celsius on Saturday. That's only 16 Fahrenheit. Into Sunday, though, getting even colder, down as low as -13. That's only 9 Fahrenheit. As we look across the western side of Europe for the weekend, Oslo there stays around freezing in Celsius on Saturday and Sunday. That's 32 degrees Fahrenheit. Well, taking a look at Saturday then, certainly some unsettled weather, some surprisingly unsettled weather in the Mediterranean for this time of year. It does mean for Mallorca it's going to be rather chilly. Temperatures will only be around 15 Celsius, and in the wind it's going to feel even cooler than that. Bye for now.
Now we can use a simple formula to convert temperatures between the Celsius and Fahrenheit scale. We've set out the problem like a typical exam question, so you can work through it step by step before looking at the solution. The formula for converting Celsius to Fahrenheit is given by F equals 9/5 times C plus 32, where F is degrees Fahrenheit and C is degrees Celsius. There's also a quick approximate way of converting to Fahrenheit. It's given by the formula F1 equals 2C plus 30, where F1 is an approximate Fahrenheit value. Question 1. In our weather report, the last temperature given was 15 degrees Celsius. What is this in degrees Fahrenheit? Question 2. Rearrange the formula to make C the subject. Question 3. Using the approximate formula, what value do you get for F1 if C equals 30 degrees? Question 4. What is the difference between the approximate temperature F1 and the real temperature F at 30 degrees C? Question 5. By putting F equals F1, find the value of C for which the approximate temperature F1 is equal to the real temperature F. Stop the tape now if you want to take the questions down and work through them on your own. Play on for the solutions. The first question was find the value of F when C equals 15 degrees. If C equals 15 degrees, then the value of F is given by F equals 9/5 times 15 plus 32. Since 15 divided by 5 is 3, F equals 9 times 3 plus 32. So F equals 27 plus 32, or 59 degrees. The second question was rearrange the formula to make C the subject. To make C the subject, we must find a way of rewriting the equation so that C is isolated or on its own. Starting with F equals 9/5 times C plus 32, we subtract 32 from both sides to get F minus 32 equals 9/5 times C. Multiply both sides by 5 to give F minus 32 all times 5 equals 9C. Then divide both sides by 9 to give 5 times F minus 32 all over 9 equals C. We've now isolated C. And with an equation, though of course not with an inequality, it's okay to write it the other way round. So we can write c equals 5 times f minus 32 all over 9. As a quick check, you can use the earlier answer for 15 degrees C. Substituting 59 for f, we get c equals 5 times 59 minus 32 all over 9. Doing the subtraction in the brackets first gives c equals 5 times 27 over 9, which cancels down to 5 times 3. So the formula gives c as 15 degrees, which is what we expected. Our formula for converting to Celsius checks out. The third question was using the quick formula, what is the approximate value f1 when c equals 30 degrees? The formula is f1 equals 2c plus 30. Substituting 30 for c gives f1 equals 60 plus 30 or 90 degrees. The fourth question was find the difference between the approximate value f1 and f when c equals 30. When c equals 30, f equals 9 over 5 times 30 plus 32, which equals 9 times 6 plus 32, which equals 54 plus 32 or 86. So f equals 86 degrees if c equals 30 degrees. So the difference between the approximate value f1 when c is 30, 90 degrees, and the value of f, 86 degrees, is just 4 degrees. The last question asked us to find the temperature in Celsius at which the approximate Fahrenheit value f1 equals the true value f. If we put f equals f1 to find c, then the true conversion formula, 9 over 5 times c plus 32, is equal to the approximate formula 2c plus 30. To solve the equation for c, first take 30 from both sides, giving 9 over 5 times c plus 2 equals 2c. Multiplying both sides by 5, remembering the brackets, to give 5 times 9 over 5 times c plus 2 equals 5 times 2c. Removing the brackets, we get 9c plus 10 equals 10c. Now, subtract 9c from both sides to find c, and we get 10 equals c. So c equals 10 degrees. So the value at which the approximate formula for the conversion gives the correct value for f is 10 degrees Celsius. You can check this by finding f and f1 when c equals 10. Using the true conversion formula, we get f equals 9 over 5 times 10 plus 32, or 18 plus 32, or 50 degrees. Using the approximate formula, we get f1 equals 2 times 10 plus 30, or 20 plus 30, or 50 degrees. So the two values check. Whether we use the true or the approximate formula, the Fahrenheit value corresponding to 10 degrees Celsius is 50 degrees Fahrenheit. That's the end of the section on notation. Next, equations themselves. An equation is an expression where the two sides are equal, but only for certain values of the unknown letter. For example, if 3x plus 1 equals 16, the two sides are equal for only one value of x. That's when x equals 5, because 3 times 5 plus 1 equals 16. So we say that x equals 5 is a solution of the equation 3x plus 1 equals 16. Solving equations is a major part of the work of scientists and engineers. Indeed, anyone who uses algebra to solve problems. Mathematicians have developed methods to solve a whole range of different types of equations. In this section, we'll look at 3 different types: linear equations, simultaneous equations, and quadratic equations. First, linear equations. Linear equations are the simplest type of equation to solve. 3x plus 1 equals 16 is a linear equation. Linear equations are called linear because their graphs are straight lines. Y equals 3x plus 1 is a linear equation. Its graph is a straight line. We're going to look at a situation in which linear equations are set up to solve a practical problem. Record companies know that when they produce CDs, it's going to cost them a lot to make the master disc before they get any profit back from the sales. This next clip shows how they might use graphs to work out how much it costs to produce 1,000 or 2,000 CDs and how many they might expect to sell to break even. It also shows how you can find these results by solving simultaneous equations.
So finally, here it is, the compact disc that you and I can play. But what about cost? Well, when the shops have taken their cut and you've paid for distribution and marketing, each disc produced has cost £6. To produce their first 1,000 discs will cost EMI £6,000. That's $12,000. But remember, we need to add on the recording studio and master disc costs. So far then, the bill comes to £58,000. For 2,000 discs, the manufacturing and distribution cost increases, but the studio and master costs remain the same. So for 2,000 discs, it costs £64,000. And 3,000 will cost £70,000. We can go on adding discs, but the important point is the initial costs remain fixed. Although using tables is an accurate way of displaying cost, it doesn't allow EMI to calculate expenditure on any other number of CDs apart from those in the table. It's much more convenient for EMI to illustrate the information graphically. We know 2,000 discs will cost £64,000. Our graph needs to show a connection between these two figures. We can place a point on the graph for each pair of numbers. But do you think a graph presented in this way is useful to EMI? Well, at a glance we can see the dots go higher as EMI produce more discs. But suppose they wanted to know the cost of 7,200 CDs. 7,200 isn't on our table of values, so there's no dot on the graph. We could calculate the cost of producing anything from 1 to 10,000 discs, but it's far easier to draw a line between all the points. Now EMI can see at a glance the cost of making any number of CDs. But that's not the end of the story. The record company have spent large sums of money just to produce one single. They aim to recover that cost and make a profit in the price of the compact disc. EMI can expect to get £10 for every CD sold, so our sales graph will look very different.
Let's have another look at the CD graphs. The yellow line gives the cost of producing the CDs. The blue line gives the money from sales. So to break even, the company must find where the cost graph and the sales graph cross. Just by looking at the graph, estimate how many CDs you think must be sold to break even. If you look at where the lines cross, the number of CDs on the graph is about 12. But remember, this is in thousands, so the number of CDs that must be sold to break even is about 12,000. Remember, this is just an estimate. Another way to find the answer is by using algebra to solve the simultaneous equations. The following equations will allow us to find the number of sales needed to break even. First, find the cost, C, of producing X number of CDs. Then find the amount of sales, S, of X number of CDs. Now for the answers to that cost equation. We know it costs £52,000 for the master disc, and it costs £6 for each disc. So, for X number of discs, the production cost in pounds is 6x. The total cost, C, for X number of discs equals the cost of the master disc plus the production cost of X discs. Therefore, C is equal to 52,000 plus 6x. And the answer to the sales equation. If X number of discs are sold at £10 each, then the total sales in pounds are 10x. S is equal to 10x. So to break even, costs must be equal to sales. C must be equal to S. 52,000 plus 6x must equal 10x. We need to find X, the number of CDs. So we subtract 6x from both sides to get 52,000 equals 4x. Divide both sides by 4. 52,000 divided by 4 equals X. The number of discs sold to break even is 52,000 divided by 4, which equals 13,000 discs. From the graph, we estimated that 12,000 discs sold would give the break-even point. This was an estimate. The accurate figure, found by solving the equations, is 13,000 discs. That's the end of the section on linear equations. Next, a closer look at simultaneous equations. In the next sequence, simultaneous equations are used to solve a practical problem.
Anyone for tea and coffee? Oh, I'd love a coffee, please.
It's tea break in the GCSE Maths Bitesize production office.
Another tea and another coffee. 3 coffees, 2 teas. Coffees and 2 teas, please.
270, please.
The 3 coffees and 2 teas cost a total of £2.70.
Here's your teas and coffees, guys.
Oh, lovely, thank you. Oh, thanks. How much do I owe you for a tea?
Thank you. How much do I owe you for a coffee? Well, they all cost £2.70, so...
There's not enough information to solve the problem, yet.
I've got 4 teas and 2 coffees. Any takers?
The total cost of these drinks is £3. So we now know that 3 coffees and 2 teas cost £2.70, 2 coffees and 4 teas cost £3. Enough information to set up a pair of simultaneous equations. The first time, it's 3 coffees plus 2 teas equals £2.70. The second time, it's 2 coffees plus 4 teas equals £3. They can be written as 3c plus 2t equals 2.7 and 2c plus 4t equals 3. Both these equations are linear equations. We want to find the price of a tea, T, and the price of a coffee, C, that fits both equations at the same time. This is why they're called simultaneous equations. Simultaneous equations allow you to find the value of two unknowns. There are two ways to solve these equations. One uses algebra and another method uses graphs. In your exam, it may tell you which method to use. Otherwise, you can choose the one you like best. The algebra method involves getting the same number of one of the letters in both equations. Then we can take the second equation away from the first and one of the letters will disappear. Then we're left with an ordinary linear equation which we know how to solve. So how does it work? If we multiply the first equation by 2, which means multiplying everything in the first equation by 2, then we will have 4t in both equations. We can now take away the second equation from the first, part by part, to get 4c equals 2.4. So c equals 2.4 divided by 4, that's 0.6. In other words, each coffee costs 60p. We can now work out how much a tea costs by putting the price of coffee we've just worked out into one of the original equations. We'll choose the first one. 3c plus 2t equals 2.7. That becomes 1.8 plus 2t equals 2.7. Taking 1.8 from both sides, 2t equals 0.9, 1t equals 0.45. So each tea costs 45 pence.
So, you owe me 45p for a tea and 60p for a coffee.
In practice, you could have just looked at the price list, but this illustrates a type of equation which has interested mathematicians for thousands of years. Simultaneous equations can be more difficult if they have negative numbers or if they have to be rearranged, and you'll come across these in the intermediate or higher tiers. This example has both these difficulties. First, we have to rearrange the equations so that they are in the form first letter part plus or minus the second letter part equals a number. In the first equation, we add 2x to both sides and turn it into the correct form. In the second equation, add 9.1 to both sides. So the two simultaneous equations are in the form we need. If we multiply the first equation by 2 and the second equation by 5, then there will be 10y's in each equation. Notice that 10y in the second equation is negative, so to get rid of it, we need to add the two equations. We're left with 4x plus 15x, that's 19x on the left-hand side, and 40 plus 45.5, that's 85.5 on the right-hand side. The y's have disappeared. That means x is 85.5 divided by 19, that's 4.5. Now don't forget to put this value back into the first equation. So 2 times 4.5, that's 9 plus 5y is 20. Take 9 away from both sides, so 5y is 11. So y must be 11 divided by 5, which is 2.2. So we have a solution. X is 4.5 and y is 2.2. It's good practice to check these solutions by testing them in the second original equation. 3 times 4.5 minus 2 times 2.2 equals 9.1, or 13.5 minus 4.4 equals 9.1. Correct. Let's recap on the procedure for solving simultaneous equations. First, multiply one or both equations to get the same number of one of the letters. Then add the equations or take one away from the other so that one letter part disappears. Then you can solve the linear equation you're left with containing only the one letter. Then put the value of the letter you've just got back into one of the original equations to solve for the second letter. Next, quadratic equations, which you need for the intermediate and higher tiers. Quadratic equations have a square in them, like a squared, b squared, y squared, or x squared. For example, if x squared equals 9, what is the value of x? Clearly, x equals 3, because 3 squared equals 9. But that's only one answer. X can also be negative 3, because negative 3 squared is also 9. The most general type of quadratic equation has a part with x squared, a part with just x, and another part which is just a number. It isn't possible to solve just by looking. Quadratic equations are normally set out with the x squared part first, then the x part, then the number part, and the whole lot is equal to 0. If you get one different from this, start by rearranging it into this form. In general, quadratic equations have two alternative solutions. Quadratic equations are so important that there are 4 different ways of solving them. The neatest way is to factorise. If that doesn't work, then we can use a more complicated method called completing the square. The most general method is to use the quadratic formula. Finally, if all else fails, we can use trial and improvement. First, factorisation. To solve the equation x squared plus 5x plus 6 equals 0, we can factorise. That means putting the expression into 2 brackets. We can work out that both brackets must start with an x, because the first term is x squared. The numbers in the 2 brackets must also multiply to make 6, and add together to make 5. That means the numbers must be 2 and 3. We can check the factorisation by multiplying out the brackets to get back to x squared plus 5x plus 6 equals 0. Now, if x plus 2 times x plus 3 equals 0, then either x plus 2 must equal 0 or x plus 3 must equal 0. That means that either x equals negative 2 or x equals negative 3. You can check that by putting these values back into the equation. As this is probably the best method, let's do one more. Solve x squared minus x equals 20. First, the equation has to be rearranged into the correct form, with everything on the left-hand side, so that x squared minus x minus 20 equals 0. To factorise, we need to put the expression into 2 brackets, each starting with an x. Then we need 2 numbers that multiply to make negative 20 and add to make negative 1. Don't forget, if there is no number in front of the x, it must at least be multiplied by 1. The numbers must be 4 and negative 5. Let's try them out. 4 times negative 5 makes negative 20, and 4 plus negative 5 makes negative 1. That means that either x plus 4 equals 0 or x minus 5 equals 0. So the 2 alternative solutions are negative 4 or 5. Remember that these are alternative solutions. Although factorisation is the most popular method of solving quadratic equations, it's sometimes difficult to work out which 2 numbers multiply and add to give the result you want. So, on to the next method. Next, completing the square. which is for the higher tier only. We'll apply this method to the equation we used before, x squared plus 5x plus 6 equals 0. With completing the square, our aim is to get something in brackets squared that equals a number. We then square root the number, leaving a simple equation to solve. In this equation, the bit in the brackets will be x plus 2.5, because when we square it, we'll get 2.5x twice, which is the 5x we need in our equation. We also get 2.5 squared, which is 6.25. That's 0.25 bigger than the plus 6 we need at the end of our original equation. So to make our new form the same as the original equation, we take away 0.25. So we have x plus 2.5 squared minus 0.25 equals 0. Rearrange that into x plus 2.5 squared equals 0.25. Now we take the square root of both sides. The square root of 0.25 is either positive or negative 0.5. This can seem odd, but check it on your calculator. So x plus 2.5 equals either 0.5 or negative 0.5. That means x equals either negative 2 or negative 3. Next, the quadratic formula, for those of you doing the higher tier. This is the quadratic formula. The quadratic formula is the solution to the general quadratic equation, ax squared plus bx plus c equals 0. Happily, you don't need to memorise it for the exam because it appears in the formula sheet that comes with your GCSE paper. In the formula, a and b are the numbers that the x squared and the x parts are multiplied by. The c is the number at the end. You have to be careful to keep any negative signs with the number. The plus or minus sign in the formula indicates that there are two alternative answers. Let's test it out on the same equation as before. In this equation, x squared plus 5x plus 6 equals 0. The a, b and c we need for the quadratic formula are a equals 1 because there's 1x squared, b equals 5 because there's 5x, and c equals 6, the number at the end. So we put these values into the formula. It's useful to put the times signs in when the letters are replaced by numbers. We can work out 5 squared, that's 25. 4 times 1 times 6, that's 24. And 2 times 1, that's just 2. Finally, we can do the 25 take away 24, which makes 1, and work out the square root of 1, which is 1. So we have two answers again. Negative 5 plus 1 over 2, that's negative 4 over 2, which is negative 2, and negative 5 minus 1 over 2, that's negative 6 over 2, which makes negative 3, just the same as before. As we only use the quadratic formula when we can't factorise, it can often involve messy calculations, so be careful with your calculator. And don't forget, you should always check your answers by putting them back into the equation to see if they come out right. Next, the trial and improvement method. Trial and improvement is a numerical method that can be used for solving quadratic and any other equations. It's long and laborious. Really, you should only use it if there isn't any other way. However, these make common questions in GCSE exams. The method is to make a first guess at what x is and put it into the equation to test it out. Then you make a better second guess and so on, keeping going until your answer is accurate enough. The difficult bit is making a good first guess, so in the exam this may be done for you. Otherwise, you need to look at the equation and choose one yourself. Let's try it out on the quadratic equation x squared plus 7x minus 9 equals 0 and find one of the solutions correct to one decimal place. We need a table to record our results. So start by trying x equals 2. Now, 2 squared plus 7 times 2 minus 9 equals 9. That's much too high, should be 0. So we'll try x equals 1. Now, 1 squared plus 7 times 1 minus 9 makes negative 1. That's too low, but very much closer. So our next guess should be close to 1. We'll try 1.2. Now we need a calculator. 1.2 squared plus 7 times 1.2 minus 9 makes 0.84, which is too high. Let's try 1.1. 1.1 squared plus 7 times 1.1 minus 9 makes negative 0.09. That's still a bit too low, but it's much closer to 0. So the best answer for x to one decimal place is 1.1. That's the end of the section on equations. Next, proportionality, for the higher tier only. We looked at the idea of proportionality in the section about using scale models to design No. 1 Canada Square at Canary Wharf in London's Docklands. In this section, we'll look at a standard method for using algebra to deal with quantities that are proportional. The GCSE questions that are set on this topic tend to follow a standard pattern that's well worth learning. The basic idea is that two quantities are in proportion if one varies according to how the other one varies. That sounds complicated. Well, it can be, so check the method carefully. The basic type of proportionality is called direct proportion. Two quantities are in direct proportion if, when one increases, the other also increases by the same proportion. For example, if you buy petrol, then the more you buy, the more you pay. If the price per litre is 78 pence, then the total price is 78 pence times the number of litres you have. We could write a formula for this. Total cost equals 78p times number of litres. Using letters, we could write it as C equals 0.78 times L, or just C equals 0.78L. We could also draw a graph to show this information, but now we have a formula, we can work out the total cost for any number of litres of petrol. Notice that the formula for our example of direct proportion is in the form first quantity equals a fixed number times second quantity. In general, we can write this as y equals k times x, where k is a constant number that links two quantities. It's called the constant of proportionality. Inverse proportion is when the second quantity gets smaller as the first quantity gets bigger. This is sometimes called indirect proportion or opposite proportion. This gives a formula of the form y equals k divided by x. The graph looks like this. Squared proportionality is when one quantity increases in the same way as the square of another quantity. This gives a formula of the form y equals k times x squared. The graph for this is an upward curve. Inverse squared proportion is when one quantity gets smaller as the square of the other quantity gets bigger. This gives a formula of the form y equals k divided by x squared. The graph for this is a downward curve. To summarise, you need to memorise these 4 formulae. For direct proportion, y equals k times x. For inverse or indirect proportion, y equals k over x. For squared proportion, y equals k times x squared. For inverse squared proportion, y equals k over x squared. Now we need to try out a question. The basic idea is that you will be told the type of proportionality. You will be told the value of the two quantities at one point. You have to find a formula connecting the two quantities and often find some more values as well. Here's an example. Two quantities A and B are in indirect proportion. When A is 20, B is 5. Find a formula connecting A and B. Use the formula to find the value of B when A is 100. Notice we're told it's indirect proportion, so we use the formula y equals k over x, or A equals k over B in this case. We are told that A is 20 when B is 5, so we can put these values into the formula to find the value of the constant k. That gives 20 equals k over 5. Multiply both sides by 5, and we get k equals 100. So we can now write our formula replacing k with 100. So now A equals 100 over B. We are now asked to use this formula to find out the value of B when A is 100. Make B the subject of the equation by multiplying both sides of the equation by B and dividing both sides by 100. So when A equals 100, B equals 1. So the procedure is, first, work out which type of proportionality is involved and choose the correct formula. Second, use the values of the quantities given to work out the value of k. Now you can write down the formula. Finally, you can use the formula to find out any other values. That's the end of our main section on algebraic methods. This section deals with sequences, graphs and loci. It's in 3 main parts: number sequences, graphs and loci. First, number sequences. This section starts by looking at some common number sequences. It goes on to explore how to find the nth term of a sequence and how to use the UN notation and recurrence relations. First, some common number sequences which you'll need for all tiers of the exam. You should be familiar with all the following sequences, as you may be asked about them in the exam. Square numbers are the squares of the counting numbers, 1, 2, 3, etc., and can be drawn as a square. 1 times 1. 2 times 2. 3 times 3. 4 times 4. So the sequence of square numbers is 1, 4, 9, 16, 25 and so on. Triangular numbers are made by adding 2, 3, 4, 5 and so on each time and can be drawn in a triangle. 1. Add 2 equals 3. Add 3 equals 6. Add 4 equals 10. So the sequence of triangular numbers is 1, 3, 6, 10, 15 and so on. For the sixth triangular number, you would need to add 6 to the previous number, giving 15 plus 6 equals 21. An arithmetic sequence is found by adding the same number each time, starting at any number you like. So 3, 5, 7, 9, 11 and so on is an arithmetic sequence starting at 3 with 2 added each time. To find the next number, just add 2. Five, 9, 13, 17, 21 and so on is an arithmetic sequence starting at 5 with 4 added each time. To find the next number, just add 4. A geometric sequence is found by multiplying by the same number each time, starting at any number you like. Two, 6, 18, 54 and so on is a geometric sequence starting at 2 and multiplying by 3 each time to find the next term. 1, a half, a quarter, an eighth and so on is a geometric sequence starting at 1 and multiplying by a half each time to find the next term. The Fibonacci sequence is a special sequence which describes a lot of patterns which occur in nature, such as the number of spikes on a fir cone or the number of petals in a flower. It's 1, 1, 2, 3, 5, 8, 13, 21 and so on. It's found by adding the 2 previous terms to get the next. So 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8. Remember, it may not start at 1, so you need to recognise the number pattern. That's the end of common number sequences. Next, for intermediate and higher tiers, how to find the nth term of a number sequence. Look at the following sequence and see if you can find the formula or general rule for the pattern the skaters make.
Watch the series of figures they make. How is this figure different from the last? And this one. What will the next figure look like, and how have the figures been formed? You might have seen the sequence made by adding one more skater to each arm of the cross. Or perhaps you saw each figure as one skater in the middle with 4 lines of skaters pivoting round her. Another way of looking at it would be to say there was one line of skaters with 2 smaller lines joined to it, and there are other possibilities. We've got just 4 figures so far, but there could be many more. What do you think the 10th figure in the sequence would look like, and how many skaters would it have? Here's one way of working it out. In each of the figures there are 4 equal arms. Each arm has 1 skater less than the figure number. So, in the 10th figure, the arms will each have 9 skaters. 4 nines are 36 plus the 1 in the middle, 37 skaters. Alternatively, you could see each arm as 10 skaters long, the same as the figure number, but all sharing skater number 1. 4 tens are 40, but because there's only one skater number 1 instead of 4, we have to subtract 3. 40 minus 3 is 37, another way of arriving at the same answer. With a bit of thought, you can create a general rule. What would your general rule be?
The answer for the 10th figure is 4 times 9 plus 1 equals 37. Or 4 times 10 minus 3 equals 37. Suppose we needed the general rule for the nth figure. Then using the second method, we now have n instead of 10 and get 4 times n minus 3 equals 4n minus 3. Suppose we tried the first method. We now have n minus 1 instead of 9 and get 4 times n minus 1 plus 1, which is 4n minus 4 plus 1 and equals 4n minus 3. In either case, we get the same formula or general rule for the nth figure, 4n minus 3. That's the end of the section on finding the nth term. Next, the UN notation and recurrence relations. You've already seen some common number sequences and found different terms. Here's one that goes 4, 7, 10, 13, 16 and so on. The first term is the first number in the sequence. A standard notation to show the first term is U1. That's U with a little 1 on the line. In this sequence, U1 equals 4. The second term is called U2. In this sequence, U2 equals 7. You've already looked at how to find the nth term of sequences like this. It goes up in threes, so the rule must have 3n in it. If the rule was just 3n, you would expect the first term to be 3 times 1, which is 3. In fact, it's 4, so 1 has been added to the 3n. This means that the nth term must be 3n plus 1. We write the nth term as un. The little n stands for the position in the sequence, the number of the term. We can use the nth term rule as a formula. For example, U5 is 3 times 5 plus 1. That's 16. Let's look at a general sequence U1, U2, U3 and so on. The term that comes before un must be the n-1th term, un-1. The term that comes after un must be the n plus 1th term, un plus 1. A different way to describe a sequence involves saying how we get the nth term from the term before it, un-1. We need to give a rule. Back to our sample sequence. Each term equals the previous term plus 3. So un equals un-1 plus 3. This method is called a recurrence relation. If we also know the first term, then we can write out the whole sequence. In our sample sequence, the first term, that's u1, is 4. We know that the next term is always the previous term plus 3. If the first term is 4, then the next term is 7. And the next term is 10. And the next one is 13, and so on. Exactly the same sequence as we had before. We sometimes need to interpret sequences that look rather different. Normally, they're just variations of what we already know. Here's one. It goes 1/2, 1/4, 1/6, and so on. You could be asked to find U4. That's the fourth term, the one after 1/6. We need to look for a pattern or something all the terms have in common. In this case, notice that all of the terms are 1 over something. They are 1 over even numbers. So U4 must be 1/8. You are certain to be asked to find the nth term, UN. Well, all of the terms are 1 over something. They are 1 over 2 times the number of the term. So it's 1 over 2 times n. In this section on sequences, you've seen some common sequences like the triangle numbers, the square numbers, and the Fibonacci sequence. You've found the nth term of sequences, and you've used the UN notation in recurrence relations. That's the end of the main section on number sequences. Next, a big section on graphs. This section looks at graphs of linear and quadratic functions and graphs of other functions. First, linear graphs. Linear graphs are the graphs of linear equations. They're called linear because they are straight lines. Y equals 3x plus 1 is a linear equation. Its graph is a straight line. The gradient of a graph is the slope of the graph. If the gradient is positive, it slopes up from left to right. If the gradient is negative, it slopes down from left to right. To find the gradient or slope of a straight line graph, divide a change in vertical length by a change in horizontal length. To find the gradient, you would divide the vertical length by the horizontal length. In this case, 2.5 divided by 2, which is plus 1.25. It doesn't really matter which values you use to calculate the changes in horizontal and vertical length. The result will always be the same. It's just easier to choose a horizontal length, which is a whole number, as this will make it easier to divide by and work out the gradient. Now watch this next clip about firing clay pots and see if you can find the gradient of each part of the straight line graph. What does the gradient mean in this case?
Because clay is basically mud, it has a lot of water and what's called organic material in it, things like plants and animal bones. They seep out of the pot when it gets heated up, so Chris has to control the temperature inside the kiln very carefully. If he raises the temperature too quickly, the water and organic material will rush out, making the pots crack, crumble, or even explode.
For the first 2 hours, it has to go up very slowly because it needs to dry out the water that's left in the pot and the organic material.
So the heat's got to be really low.
It's very low.
In the kiln.
So the water can seep through the clay very slowly. Then after that, it goes up to about 600 degrees, and then all the organic material would have burnt out. Then you can turn the kiln right up until it reaches 1,000 degrees, and then it'll be finished. The kiln will take about 12 hours to cool down, and the pot will change from this to that.
This hardening of the clay in the kiln, or biscuit firing as it's known in the trade, is the most important part of the whole process, and it relies completely on time. Chris has to know at every stage exactly how fast he can raise the temperature inside the kiln. So the rate, or how fast he increases the temperature per hour, is crucial. As you can see on this graph, Chris raises the temperature very slowly to start with, only 75 degrees centigrade per hour. So after 1 hour, the temperature is increased by 75 degrees. After 2 hours, it's climbed a total of 150 degrees. You can see this as a sloping line which gets higher as the temperature increases. Once Chris is left with pure clay, he can increase the heat more quickly, maybe 200 degrees centigrade per hour. The line becomes steeper because each hour there is a larger increase in temperature. At 1,000 degrees, he stops increasing the heat.
Did you find the gradient of each part of the straight line graph? What did the gradient mean? Watch the clip again if you're not sure. Here are the answers to check against your notes. As Cheryl said, the temperature changes 75 degrees in 1 hour, or 150 degrees in 2 hours. So at first, the gradient equals 75 divided by 1, or 150 divided by 2. In both cases, the gradient is 75, or plus 75, as the temperature increases with time and the graph slopes up from left to right. Once a temperature of about 600 degrees is reached, you can see that the gradient of the graph changes to 200 over 1, which is equal to plus 200. When Chris reaches 1,000 degrees, he stops increasing the heat, so there is no further increase in temperature and the gradient of the graph becomes 0. What the gradient describes in this case is the change in temperature per hour. For the first 8 hours, the increase in temperature is 75 degrees per hour. Between 8 and 10 hours, the increase is 200 degrees per hour. After 10 hours, the increase is 0 degrees per hour. That's the end of the section on linear graphs. Next, quadratic graphs. Quadratic graphs are the graphs of quadratic equations. We can solve quadratic equations using algebra by factorising, by completing the square, or by using the quadratic formula. We can also solve quadratic equations by drawing graphs. This can be slow and awkward to do by hand, but you must practice for your exam. Many mathematicians use a graphing calculator or graph drawing software to do this. We recommend you use tools like this to get used to what different graphs look like. We know that a linear equation always gives a straight line graph. A quadratic equation always gives a U-shaped graph. Technically, it's called a parabola. Sometimes it can be upside down. We're going to draw a graph showing x squared plus x minus 6 and use it to solve the quadratic equation x squared plus x minus 6 equals 0. First, we make out a table so we can work out some coordinates. We have a column for the values of x we'll put into the equation, and for the corresponding values of y that the equation produces, and a column for the coordinates these points will have on the graph. It's difficult to decide where to start and finish, so it's common for exam questions to tell you. We'll start at -4 and go up to +4. You would normally use a calculator to work out each value of y, so check how your calculator works. The trickiest bit is handling the negatives. Use brackets when you square a negative number. Let's do the first one. That's x equals -4. So y equals -4 squared plus -4 minus 6. So with the calculator, press bracket, -4, close bracket, squared, plus, bracket, -4, bracket, minus 6 equals. And you should get 6. That can go in the table, together with all the other values. These values give us the coordinates of the points to plot. Now to create the graph. The values of x go from -4 to +4. The values of y go from -6, the smallest, up to 14, the largest. So we can add a scale. Now plot each point carefully with a cross. That's -4, 6, -3, 0, -2, -4, -1, -6, 0, -6, 1, -4, 2, 0, 3, 6, 4, 14. When all of the points are plotted, you need to join up the points with a nice smooth curve, not with straight lines. At the start, we said we'd use this graph to solve the equation x² + x - 6 = 0. In other words, we want to find the values of x when y is 0. That is where the graph crosses the x-axis. On the graph, you can see that this happens in two places, when x equals -3 and again when x equals 2. This is exactly the same two answers we got from factorising. Now that we've drawn the graph, we can use it to solve a whole family of equations. x² + x - 6 can equal anything that will fit onto our graph. For example, if we want to solve x² + x - 6 = 5, then we draw a horizontal line where y equals 5 and read off the values of x. Reading carefully from the graph, we can see that x equals -3.9 and x equals 2.9. That's the end of quadratic graphs. This section is about plotting graphs of other functions. We've looked at linear graphs, and we've looked at quadratic graphs. In this section, we'll go on to look at the graphs of some other functions: cubic graphs, reciprocal graphs, exponential graphs, graphs of circles, and trigonometric graphs. Cubic graphs have x cubed in their equations. Reciprocal graphs have equations that start with 1 over, like 1 over x. Exponentials are graphs where x is the power, like 2 to the power of x. Graphs of circles have an equation with both the x and the y on the same side. The most common one is x² + y² = 1. Trigonometric graphs are graphs of sine, cosine and tangent. The important thing with graphs is to get a feeling for their shape. Each of the graphs you need to know about has a distinctive shape. Let's go through them. First, the cubic graph. The most basic cubic graph is y = x cubed. Notice the way it turns in the middle. It looks just like the U-shaped quadratic graph, except the left-hand side has been turned upside down. You can get more complicated cubic graphs if you add extra bits to the equation, like y = x cubed plus 6x² plus 11x plus 6. Notice that it turns twice. Remember that you can solve quadratic equations by looking at where they cross the x-axis. This graph crosses the x-axis in 3 places, where x is -1, -2 and -3. That's because we can factorise x cubed plus 6x² plus 11x plus 6 to get x plus 1 times x plus 2 times x plus 3. To help you get to know the basic shapes, here are some other cubics. Y = x cubed minus 3x. y equals x cubed plus x squared minus 12x. Notice the basic shape is now back to front. Y equals x cubed plus x plus 1. Notice that the second term has gone and we are back to the basic shape of x cubed. So cubic graphs can either have one turn and be either way round, or they can have two turns and be either way round. Now we'll look at reciprocal graphs. A typical reciprocal graph has y equals 1 over x. They have one basic shape, and it's a bit weird. The only real difference we can make is to try a negative in front and look at y equals negative 1 over x. It's the same shape, just in the other quadrants. Here are some variations. Y equals 1 over 2x is the same shape, just pushed in a bit. Y equals 1 over 3x plus 6 is the same shape, but moved over a bit. So reciprocal graphs have this basic shape, either this way round or this way round. Next, exponential graphs. Exponential graphs have a nice simple shape. This is the graph of y equals 2 to the power of x. It curves up, getting steeper and steeper as it goes. We can make it go down by introducing a negative power. This is y equals 2 to the power of negative x. Here are some variations. Notice that we can't change the basic shape much, just how steeply the graph rises. This is y equals 3 to the power of x. And this is y equals 5 to the power of x. And here's y equals 2 to the power of 2x. The one thing they all have in common is that they cross the y-axis at the same point, 0, 1. This is because anything to the power 0 is always 1. So the exponential graphs always slope up or down, getting steeper and steeper, but they always go through the point 0, 1. Next, for the higher tier, the graph of a circle. The basic equation of a circle is x squared plus y squared equals 1. The two things we can vary with a circle are where the centre of the circle is and the radius of the circle. This is x squared plus y squared equals 4. Notice that this gives a radius of 2, not 4 as you might have expected. Here's x squared plus y squared equals 9, which has a radius of 3. We can move the centre by adding something to the x and y parts. Here is x plus 1 squared plus y plus 1 squared equals 9. Notice that it moved the centre to negative 1, negative 1. That suggests that if we do minus 1 to both of them, we'll get a centre at 1, 1. Let's check. Yes! So we can put the centre where we like. To put it at the point 2, 3, we subtract 2 from the x part and 3 from the y part. Here it is. So the basic circle is x squared plus y squared equals 1. This has its centre at 0, 0 and has a radius of 1. The radius is the square root of the number on the right-hand side of the equation. So x squared plus y squared equals 4 has a radius of 2. We can move the centre by taking away the centre coordinates from the x and y parts. So x minus 1 squared plus y minus 2 squared equals 9 has a radius of 3 and a centre at 1, 2. Finally, we'll look at the trigonometric graphs sine, cosine and tangent, sine, cos and tan for short. We'll just look at the basic shapes for now. This is sine x. It's a repeating wave shape. Notice that it goes through the centre 0, 0. Also notice that it never gets higher than 1 or lower than negative 1. This is cos x, which is much the same but shifted along a bit. And this is tan x, which is just wild. It's kind of like a collection of cubic graphs next to each other. We'll say no more about these for the moment because I want to show you how to vary graphs in general first. Sine x is a repeating wave which goes through the origin 0, 0 and stays within plus or minus 1. It repeats itself every 360 degrees. Cos x is a repeating wave which crosses the y-axis at the point 0, 1. It also stays within plus or minus 1. Again, it repeats itself every 360 degrees. Tan x is a repeating pattern which goes through the origin. It repeats itself every 180 degrees. This last section on graphs will look at how we can transform a graph by applying changes to its equation. There are 4 types of transformation we'll look at. You can slide it up or down, you can slide it left or right, you can stretch it up or down, or you can stretch it in or out. The simplest graph to see these transformations on is y equals x squared. Here's the basic graph. Now let's add something to it. This is y equals x squared plus 2. That moved it up 2 units. This is y equals x squared minus 1. That moved the basic graph down 1 unit. To move it left or right, we have to add or subtract inside the function. That means do it to the x before we square it. Here's the basic graph of y equals x squared again. This is y equals x plus 2 all squared. Notice the brackets to say it is all squared. The unexpected thing is that adding makes it go to the left. This is y equals x minus 1 all squared. I hope you guessed that it would move to the right. We can put these 2 transformations together. Start with the basic graph. Let's move it up 1 unit and 2 units to the right. So we take 2 away from inside the square and add 1 at the end. That's y equals x minus 2 all squared plus 1. Now for the stretches. Again, start with the basic graph y equals x squared. Let's stretch it up and down. To do this, we multiply or divide the whole equation. This is y equals 2x squared. That is 2 times x squared. That stretched it up and down. This is y equals x squared divided by 2. That squeezed it up and down. Let's check that these ideas work for the sine and cosine graphs that we looked at earlier. Here's a basic sine graph. So let's add 1. That should make it go up 1 unit. Sine x plus 1. Taking away 1 should make it go down 1 unit. This is sine x minus 1. If we do it inside brackets, it should go left and right. Now sine and cosine apply to angles, so we can't just add 1 or 2. Instead, we need to add a whole right angle of 90 degrees to see the effect. Again, here's the basic sine graph. This is sine of x plus 90 degrees. Note the brackets and don't forget that plus means left. This is sine of x minus 180 degrees. That moves it to the right by 180 degrees. Here's 2 times sine x. That makes it stretch up and down. And here's the sine of 2x, which squeezes it left and right. It's definitely well worth getting some time with a graph drawing program or a graphical calculator so you can experiment for yourself. Here's a summary which you'll need to remember. To move the graph up or down, add or subtract something from the whole equation. To move the graph left or right, subtract or add directly to the x. Brackets are useful here. To stretch or squeeze the graph up and down, multiply or divide the whole equation. In this section, we've looked at a range of different types of graphs. You should be able to identify cubic graphs, reciprocal graphs, exponential graphs, circular graphs, and trigonometric graphs. You should also be able to transform your graphs with slides and stretches. That's the end of the section on graphs. Finally, a look at loci. A locus is the path of an object that can only move in a certain way. The plural of locus is loci. In this section, we'll look at 3 common loci. A circle is equidistant to a fixed point. The perpendicular bisector is equidistant to fixed points. The angle bisector is equidistant to 2 lines. Here are some situations in which an object is moving. Look at them and decide what shape is the path of the moving object. Then decide what features of the situation cause it to be that shape and no other. With loci, it's important to state what is fixed and by how much. There are 2 key words we need to use. We get lines or points that don't move. We call them fixed points or fixed lines. If something is always the same distance away from an object, we use the word equidistant, meaning equal distance. Let's look at the situations again. This circle is the locus of a point always at the same distance from a fixed point. This shape is the locus of a point that always stays the same distance away from the straight line. The path of this object is a straight line right down the middle between 2 fixed points, the girls' heads. It's called the perpendicular bisector of the line that joins them. The paint can falls in a straight line, always the same distance away from the 2 sides of the ladder. The paint can's path divides the angle between the 2 lines exactly in half. It's called the angle bisector. And finally, an example where the locus is a 2-dimensional shape, not a line. Imagine a cow tethered to a fixed post. The cow can eat all of the grass up to the edge of the circle and everywhere inside it. The mathematical name for a filled-in circle is a disk. These situations cover all of the common types of loci you'll need. The next step is to practice drawing them. The important thing is that you must use a ruler and a pair of compasses. This is called construction. First, we'll construct a circle with a radius of 4 centimetres. Here are two fixed points 5 centimetres apart. We're going to construct the locus of a point equidistant to these 2 points. The locus is the perpendicular bisector of the line that joins the 2 points. To construct the perpendicular bisector, first open the compasses to a little over half the length of the line. Place the compass point at one end and mark an arc on both sides of the line. Now repeat for the other end of the line. The arcs on both sides should cross. Now join up the 2 crosses. This is the perpendicular bisector. It makes an accurate right angle with the line joining the 2 points. Here are 2 fixed lines 50 degrees apart. We're going to construct the locus of a point equidistant to these 2 lines. The locus is the line bisecting the angle between the 2 lines. To draw the angle bisector, first open the compasses. Place the point where the lines meet and draw an arc on both lines. Now move the compass point to each arc in turn and draw a new arc between the lines. The arcs need to cross. Now join up the point and the cross. This is the angle bisector. It makes an accurate 25 degrees. Finally, we need to put these skills together to solve a practical problem. Here's a treasure island. We're told the treasure lies on a line equidistant from the big tree and the hilltop point. It's also exactly 100 paces from the big tree. Find the treasure. If the treasure lies on a line equidistant from the big tree and hilltop point, we need to draw the perpendicular bisector between them. It's exactly 100 paces from the big tree, so we need to draw a circle 100 paces from the tree, using the scale on the map to set the distance. There are only 2 places where the perpendicular bisector and the circle cross, and only one of these is on the island. So X marks the spot. You may have spotted a quicker way to do it, if you realise that the treasure must also be 100 paces from the hilltop point. The treasure will lie at the intersection of these 2 circles, both radius 100 paces. So in this section, we've looked at standard loci, constructed a circle, a perpendicular bisector and an angle bisector. That's the end of the section on loci, and the end of the whole section on sequences, graphs and loci. It's also the end of this programme about algebra. There are other maths programmes about number and measures, and shape, space and data handling. And don't forget, there are also the GCSE Bitesize books, and the GCSE Bitesize website at www.bbc.co.uk/revision, where you'll also find an interactive maths test so you can quickly check what you know.